So let's talk about our last advanced theory of covalent bonding, and that is molecular orbital theory. So Vesper theory and valence bond theory are great theories to predict the bonding arrangement in molecules based upon their Lewis structure. Valence bond theory uses orbital overlap of atomic orbitals to predict what type of bonding interaction occurs. Either it be a sigma interaction if it's a head-on overlap of atomic or hybrid orbitals, or a side-by-side overlap, which occurs between adjacent p orbitals. So that does a good job, predicting and distinguishing single bonds from double bonds from triple bonds. But when we combine atomic orbitals and make molecules, they're no longer atomic orbitals. Now they are molecular orbitals because we made a molecule. And so that's what an molecular orbital is. It results from the combination of atomic orbitals or hybridized orbitals. So I'll just make a note of that. So or hybrid orbitals. So when we have these interactions, either it be a sigma or a pi interaction, once we combine those atomic or hybrid orbitals, we make molecular orbitals, so a new type of orbital. So here is a molecular orbital diagram, or, we're combining atomic orbitals to make a diatomic hydrogen atom. So we take the atomic orbitals from each of the hydrogen atoms. All right, so there's an electron in a 1s orbital on one hydrogen and another electron in a 1s orbital on the other hydrogen. So we bring together two atomic orbitals. So in this case, we're bringing two atomic orbitals. And when we bring them together to make a molecule, we make two molecular orbitals. So kind of like how we made hybrid orbitals. It's the number of atomic orbitals you put in equals the number of hybrid orbitals you get out. So it's the same thing here with molecular orbitals. The number of atomic orbitals you put in to making a molecule, you get two different molecular orbitals out of it. The only difference is when talking about hybrid orbitals, we said all of those orbital energies were degenerate, or the same energy. That's not the case for molecular orbitals. When you do a linear combination of atomic orbitals, you actually get molecular orbitals with two different energies. One where constructive interference happens, and then one where destructive interference happens. So when we combine two atomic orbitals, we get a bonding molecular orbital and an anti-bonding molecular orbital. So there's 1, 2 MOs that come out of combining two atomic orbitals. So that's what I want you to see here, is that the number of atomic orbitals you put in equals the number of molecular orbitals you get out. All right, so let's look at the details of these molecular orbitals: bonding and anti-bonding molecular orbitals. So this was just kind of like an introduction to it. All right, so what is MO theory, or molecular orbital theory? This type of theory considers the mathematical linear combination of atomic orbitals when we bring atoms together to form bonds. But when we form bonds, we form molecules. So we generate molecular orbitals that actually can encompass or explain the entire molecule rather than the individual atoms and their atomic orbitals. So, like I said, the number of atomic orbitals you put in equals the number of molecular orbitals you get out. This is like super important, so I'm going to write it down. So number of atomic orbitals in equals number of molecular orbitals out, just like when we were talking about hybridization. So there's three different types of molecular orbitals that we can get out of this combination. We can either have MOs that are bonding in character. This is where we can strengthen bonds by putting electrons in it, and we can form bonds, like in our sigma overlap or our pi overlap type of interaction. We can have anti-bonding molecular orbitals that have anti-bonding character. This weakens bonds. And then we can have non-bonding molecular orbitals. So non-bonding electrons, these are where our lone pairs reside. And so MO theory addresses some of the limitations of Vesper theory that valence bond theory could not do. So if we think back to our limitations, we did address, differentiating single, double, and triple bonds using valence bond theory. So we did that. But what MO theory can do in addition to Vesper and valence bond theory is that we can predict paramagnetism and diamagnetism. VSEPR theory couldn't do that. We can also predict whether a compound exists or not. This is through calculating bond order. So a bond order, if you calculate using MO theory a bond order of 0, then the molecule does not exist. Does not exist if the bond order is 0, and we'll get to that. And also what you can do using molecular orbital theory is colors of compounds, which is pretty cool. That's where a lot of inorganic chemistry comes into play. You can see cool colors of different transition metal compounds. All right, so let's think back to the different types of molecular orbitals that I just introduced right now. So in MO theory, when we use MO theory, we're thinking about wave nature of electrons. So, I've drawn the atomic orbitals coming together. We've thought of those electrons as particles in VSEPR theory and drawing Lewis structures, but in MO theory and even valence bond theory, we think about orbital shapes. Those shapes are due to the wave nature of electrons. And so when we combine waves, you get constructive, they can interact constructively, or they can interact destructively. That's like if you have a very still lake and you drop two pebbles into the lake at the same time, each pebble like creating a wave of water. And so when you drop two pebbles in at the same time and those waves interact with one another, you get places where those waves can add up constructively to make a larger wave, or those waves can cancel each other out. That's where it's interacting destructively. So just like pebbles producing water waves, electrons, if you think of them as waves, can also interact constructively or destructively. And so if you think of electrons as waves, when an electron wave interacts constructively, the resulting molecular orbital, so if you think of the waves as our atomic orbitals, if those atomic orbital waves interact constructively, the resulting molecular orbital is lower in energy, meaning more stable. So if it's more stable, this is a bonding orbital. So bonding orbitals, when you place electrons into it, we strengthen the bond overall. All right? Okay, so that's when waves interact constructively. When waves interact destructively, so we're bringing together two atomic orbitals that are waves, they interact destructively. This results in a new molecular orbital that's higher in energy. So this, we denote antibonding waves with an asterisk. All right. So typically, when we're talking about a bonding orbital, we would call it sigma. All right, for our sigma interaction. And then the counterpart antibonding orbital would be sigma star. And so that means a sigma antibonding orbital. So if you put electrons in an antibonding orbital because it's higher in energy than it started originally, when you place electrons into this should say antibonding, in antibonding MO, then it weakens the bond overall. And so if we think back to Aufbau's principle and Hund's rule, how we fill electrons, bottom up to the most stable to increasing energy, as we add more electrons to a molecule, it is possible to start adding electrons to antibonding orbitals and weaken the bond overall. So keep those rules in mind when adding electrons to a molecular orbital diagram. You always fill up bottom to top. So let's look at an MO diagram for a hydrogen atom. So this is the MO diagram for diatomic hydrogen. So H2, MO diagram. So hydrogen only has a 1s electron. That's it. So it's the simplest case because there's only one electron to take into account. So we have two different atomic orbitals coming together. So in this column, you see the atomic orbital for the hydrogen atom. This is the atomic orbital. And then we see another atomic orbital for just the single hydrogen atom on the other side, the other part of the diatomic molecule. So in the center column here, this is our molecular orbital, because when we bring together atomic orbitals, we make molecular orbitals, wherein we make our H2 molecule. So like I said, when you bring together two atomic orbitals, we have to get two molecular orbitals out. So two atomic orbitals in equals two molecular orbitals out. So that's what you see here in this middle column. These are all the MOs, all right, what's in orange. So you see our bonding orbital that's stabilized at the bottom. This is our bonding. And then up here is our antibonding. We have to make two molecular orbitals because we put into atomic orbitals. And so if we follow our rules up here, waves that interact constructively result in orbitals that are lower in energy. So this is our bonding. These are our bonding orbitals. And then the deconstructive interaction, these are our antibonding orbitals. So that's what you see here. We see our bonding down here and our antibonding up here. So if we take inventory of all of the electrons that come from atomic orbitals from for our hydrogen molecule, there's a total of two electrons that are coming from atomic orbitals. So now we can place those electrons in our molecular orbitals that we just produced, because it's the interaction of atomic orbitals. So we're just rearranging these electrons to make the molecule. So we had two electrons in those atomic orbitals, so we need to place two electrons into our molecular orbitals. So that's what you see here. Since we're placing two electrons in our MO, we're going to follow Aufbau's principle and fill bottom to top. So we want to place those two electrons in the lowest levels first before we start filling them up top. And so what you see here is each of these boxes represents an orbital, and so an orbital can hold two electrons. So there's where those two electrons come from. And so those two electrons that are occupying a bonding orbital signifies the bonding sigma interaction, the single bond between those two hydrogen atoms. So this is just a different way, MO theory is just a different way to interpret covalent bonding in molecules. And so how we denote that this is a bonding orbital is we're saying that there are two electrons in a sigma type interaction between 1s orbitals between these hydrogen atoms. So that's what this letter or Greek letter indication is that this is a sigma interaction because it's a sigma interaction between two head-on s orbitals. And there's two electrons in it, so there's our sigma bond that we need to make the single bond between our hydrogen molecule. All right, so how can we figure out from the MO diagram that the hydrogen-hydrogen interaction is a single bond or a bond order of one? I mean, we know when we draw out the Lewis structure of diatomic hydrogen that it's a single bond, but the MO diagram also, we can calculate that it's a single bond as well. And so when we form the diatomic hydrogen molecule, what I want you to note here is that the bonding orbital, that this bonding interaction is even lower than energy than our atomic orbitals of hydrogen because of the constructive interaction between those two atomic orbitals. So yeah, following Aufbau's principle, we need to occupy this lowest orbital first. So what this also tells us is that a diatomic hydrogen molecule is more stable than hydrogen atoms just, with one unpaired electrons floating around. So this is why in nature, when our elemental hydrogen exists, it exists as an H2 molecule because of this MO theory telling us that the combination of atomic orbitals results in a lower energy orbital and a higher energy antibonding orbital, but due to the number of electrons that exists in hydrogen, they occupy all bonding orbitals. And so that's why H2 exists in nature, and we can calculate that it exists through its bond order, and we'll eventually get a bond order of 1 for hydrogen, and that will corroborate our Lewis structure for our diatomic hydrogen. So so like I said, when you form H2, it forms because the molecule is more stable when you actually form the molecule than two separate hydrogen atoms. So that's what I kind of showed here, that forming the H2 molecule is more stable than just leaving the hydrogen atoms with unpaired electrons floating around in space. And that's because of the stabilization we get when combining atomic orbitals. So if we write out the electron configuration for the H2 molecule, for the molecule itself, we want to say instead of like one electron in a 1s orbital, we actually want to say we have two electrons, because there's two electrons from two different hydrogen atoms in a sigma 1s molecular orbital. So how we write that is like this. So this is another way to write electron configurations for molecular orbitals. Molecular orbitals are sigma pi interactions. So in this case, we want to say that there are two electrons in a sigma interaction between 1s orbitals in the hydrogen molecule. So this molecule has a bond order of 1. We know that from the Lewis structure, but there's actually a calculation you can do to determine the bond order of any molecule. So the bond order of any molecule is take the number of electrons in bonding orbitals, subtract any electrons in antibonding orbitals, and then divide by 2, or times 1/2. So bond order equals number of electrons in bonding, MOs minus number of electrons in antibonding, and then just divide by 2. That's a weird looking 2. All right, so for hydrogen, if we look back at this, there are two electrons in our bonding orbitals. There's 0 electrons in our antibonding. So to calculate bond order for hydrogen, it's 2 minus 0 divided by 2. So our bond order for hydrogen is 1. And that makes sense because the Lewis structure says that diatomic hydrogen has a single bond. So MO theory is just kind of agreeing with everything that we've already learned thus far. So let's look at some other molecules where the bond order is a little bit different. By calculating bond order, we can determine whether a molecule exists or not. Because if a bond order is 0, then that means that the bond, it's not favorable to make the bond at all, according to the MO diagram, and so that molecule won't exist. So let's see if diatomic helium exists. So really the question we're asking is, if we form the H2 molecule, is helium-2, diatomic helium, is that more stable than just having two helium atoms separate in space? So if we draw out the MO diagram for two helium atoms, just like we did for hydrogen, the skeleton structure of our MO diagram actually stays the same. If we combine, if we look at the electron configuration for a helium atom. So helium is 1s2. So we have two electrons in a 1s orbital. So that's what you see right here. But we're going to bring together two helium atoms. So when you combine two different 1s atomic orbitals, so we're combining two atomic orbitals, we need two molecular orbitals out. So two atomic orbitals in equals two molecular orbitals out. So we're going to make a bonding. I said bonding, but I drew antibonding. We're going to draw a bonding orbital first and an antibonding. All right, where bonding is more stable than antibonding. So to describe this interaction, this lower box is our bonding orbital. It's a sigma interaction between 1s orbitals. Up here, this is our antibonding, so it's sigma star 1s. So there's the skeleton structure of our MO diagram. If we look at how many electrons we need to place, there's a total of 4 electrons in our atomic orbital. So we need to place 4 electrons in our molecular orbitals we just made. So again, following Aufbau's principle, let's fill bottom up. So 4 electrons, 1, 2, 3, 4. So there's our MOs. So let's write out the electron configuration, the MO electron configuration for diatomic helium. So we're looking at the middle column. We need to say where all of the electrons are. So I'll start at the bottom. So I see that there's 2 electrons in a sigma molecular orbital, sigma 1s. There's 2 electrons there. And then we have some other electrons up here. We need to take inventory of 2. So sigma star, it's an antibonding orbital, 1s, and there's 2 electrons in there too. So that's it. There's only 4 electrons. So there's the electron configuration for diatomic helium. So if we want to calculate the bond order, so remember it's up here. It's number of bonding electrons in bonding orbitals minus number of electrons in antibonding orbitals divided by 2. So if we calculate this, number of electrons in bonding orbitals, 2. Or you could look in the electron configuration. So there's 2 electrons in bonding orbitals. So 2. Do a different color. 2. And then number of electrons in antibonding orbitals, so that's 2. Or 2. So 2 minus 2 over 2. It equals 0. So the bond order for diatomic helium equals 0. So that means that diatomic helium is not a stable molecule. Therefore, He2, or diatomic helium, does not exist. So it doesn't exist. So this is kind of showing you why helium just exists as a single atom out in the natural world. Helium exists as monoatomic because there's no energy payback. We don't make a more stable substance by making H2. That helium is perfectly okay just being a monoatomic atom. We don't get any energy payback or any stability by making a diatomic molecule like we did for hydrogen. When we made diatomic hydrogen, we do make a stable molecule because the bonding orbital, where all of the electrons are, is in a more stable configuration than just hydrogen atoms as a monoatomic atom. But in this case, for helium, there's no energy difference. So diatomic helium is not a stable molecule. Bond order is 0, that there's no driving force to actually create that bond. So there's a lot of different orbitals that we've talked about in this chapter. So let's just do a quick overview of all the different types of orbitals we've talked about. Atomic orbitals, hybrid orbitals, and then now molecular orbitals. So atomic orbitals come from atoms. So the letter designations when thinking about atomic orbitals, these come from atoms. So off of the periodic table, when thinking about atomic orbitals, these are our S, P, D, F, etc. Those are all atomic orbitals. You think about an atom and the shape or the electron probability of finding an electron in a certain space. Either is it in a sphere, is it in a dumbbell p orbital shape, or is it in a butterfly looking d orbital? So those are our atomic orbitals. You want to look for letters like S, P, D, F. That's what we use to write electron configurations for atoms. You know, for like manganese here, we have argon 4s2 3d5. We are telling you where the electrons exist on an atom in their atomic orbitals, SPD type shapes. Hybrid orbitals, which we talked about with in valence bond theory, originate from combining atomic orbitals to get hybrid orbitals. So when we combine atomic orbitals to make those new shapes we need, like tetrahedral, trigonal pyramid, all those things, we combine atomic orbitals to get the same number of hybrid orbitals out. We've already talked about that. Number of atomic orbitals to hybridize equals the number of hybrid orbitals you make. So if we put together an s orbital and 2 p orbitals on a carbon atom or something, we get 3 unique sp2 hybrid, hybrid orbitals. So hybrid orbitals are just combinations of atomic orbitals. Now, molecular orbitals originate from combining adjacent atoms. So when you combine either atomic orbitals on different atoms or hybrid orbitals on different atoms, you make molecules because you're combining different atoms to make molecules. Both atomic and hybrid orbitals, these are applied to just singular atoms. So these two are applied to atoms. So to a single atom, while molecular orbitals are made when you combine adjacent atoms to make bonds, when you make molecules. So molecular orbitals come from the combination of different atomic hybrid orbitals on adjacent atoms to form bonding and antibonding orbitals. Molecular orbitals describe bonds between atoms. So the types of things that you want to look for with for molecular orbitals are things like sigma, because this describes a bond or a type of interaction. So you can see something like sigma 1s, or you can see something like pi 2p. These represent MOs, sigma and pi. Those are the ones you're going to see. And so for hybrid orbitals, you'll see things like sp2, sp, sp3, sp3d2, things like that. So those are hybrid orbitals, while atomic orbitals are things like spdf. While molecular orbitals, you're looking for symbols like sigma and pi. All right, so that kind of just overviews all of the different orbitals. I know we've talked about a lot in this chapter. All right, so let's kind of move on and think about other molecules and whether they exist. So let's look at diatomic lithium and diatomic beryllium. So now we're moving on to period 2 elements. So with period 1, when we looked at hydrogen and helium, we only worried about the 1s. But now looking at lithium and beryllium, we've now expanded to the n equals 2 principal quantum number. So now we've made these molecules bigger. We have to worry about more atomic orbitals now. We have to worry about the 1s and the 2s orbital. So let's kind of look at this. So does diatomic lithium, diatomic beryllium exist? So let's first just take inventory of all of the electrons in lithium and beryllium. So lithium, well, it has lithium has 3 electrons. So in diatomic lithium, there's a total of 2 times, because there's 2 lithium atoms, 2 times 3. So there's a total of 6 valence electrons. In beryllium, because it's element number 4, it's 2 times 4. So there's a total of 8 valence electrons. We're just taking inventory because their MO diagrams will look the same, just different number of electrons. So let's look at the MO diagram for lithium. So for lithium, a lithium atom is a 1s2, 2s1 electron. So we have 2 atomic orbitals we need to worry about when bringing 2 lithium atoms together. The electrons in its 1s shell and in its 2s shell. So we have 2 different interactions here, essentially 2 MO diagrams kind of on top of one another. Here's the 1s interaction, and here's the 2s interaction. And you see that there's the correct number of electrons there for the 2 lithium atoms. So what you see here is we have 2 different interactions. We have our 1s and our 2s. Both of them are sigma interactions because they're just completely spherical s orbitals, and they do a head-on sigma type interaction. And so you see in both of these cases, between the 1s, we have our antibonding and bonding cases, where our bonding is sigma 1s because it's a sigma interaction between 1s orbitals. And then we have our sigma antibonding between 1s orbitals. And so that's what that star antibonding means. Then we see the same thing for our 2s atomic orbitals. Bring those 2 atomic orbitals in, you get 2 molecular orbitals out. So we have also a sigma interaction because they're still s orbitals, but now they are between 2s atomic orbitals. Right, so we see that bonding orbital is stabilized, and then the anti-bonding counterpart is destabilized. And so you see sigma star 2s, all right? And so now for lithium, let's place those 6 valence electrons. So in the atomic orbitals, you can count here, there's 6 that we need to place. So fill bottom to top. So 1, 2, 3, 4, 5, 6, all right? And so what you see here, if we calculate bond order for lithium, for diatomic lithium, we see that there's a total of 1, 2, 3, 4 electrons in bonding orbitals, minus there's 2 electrons in antibonding orbitals over 2. So our bond order is 1. So bond order for, it's up down here. So bond order equals 4 minus 2 over 2 equals 1. So diatomic lithium should exist. But one thing I want you to kind of note here is since we do bonding electrons minus antibonding electrons, you see that these inner core electrons, they actually just cancel out. There's 2 electrons in bonding, 2 electrons in antibonding. So these actually just cancel. When doing your bond order calculation, they cancel. So if you only just count the valence electrons when considering the bond order, so we could kind of do this again, bond order equals 2 minus 0 over 2, you also get 1. So here is another reason why when we think about bonding and chemical reactivity, we only consider valence electrons, because when drawing out the MOs, we see that all of the inner shell electrons cancel. bonding and antibonding. So we don't really have to consider writing this. When we draw MOs, we only have to draw valence shell electrons. Isn't that nice? Okay, so let's predict the bond order for beryllium. So the MO diagram will look the same for beryllium, different color. So let's just change this to beryllium. Beryllium, each atom has 4 electrons, so all we really need to do is just add another electron. So there's a total of 8 electrons we have to place for diatomic beryllium. So 1, 2, 3, 4, 5, 6, 7, 8. Whoops, they're spinning the same way. That's not going to happen. 7, 8. All right, so beryllium just has, this molecule has just 2 extra electrons. So if we calculate bond order, we can see, again, if we just kind of worry about valence shell electrons, because we know that these ones cancel, we see that there's 2 electrons in bonding orbitals in the sigma 2s, and then there's 2 electrons in the sigma star antibonding 2s orbital. The 2 minus 2 over 2 equals 0. So bond order for beryllium, diatomic beryllium, is 0, so this molecule does not exist. But lithium, diatomic lithium, should exist because it has a bond order of 1. So for these lithium and beryllium examples, we've expanded our valence shell to the 2s subshell. So let's look at the other elements past beryllium, where we have to now introduce the 2p subshell. So if we think about the molecules diatomic boron to diatomic neon, these we have to now consider 2p orbitals, our p orbitals. So these interactions between p orbitals are different than s orbitals. S orbitals only ever have sigma interactions. So their MO diagrams were a little bit simpler because you brought 2 atomic orbitals in and then you got 2 MOs, like one up, one down. But with p orbitals, it's a little bit different because p orbitals are directional and we can have different ways that they combine. And so we need to consider, if we want to be able to inspect diatomic boron, carbon, nitrogen, oxygen, fluorine, and then neon, we need to consider how do molecular orbitals between p atomic orbitals, how do they combine? So p orbitals can combine 2 different ways, either end-to-end. So an end-to-end overlap, we know, is a sigma interaction. It's a head-on type of interaction. So end-to-end overlap occurs between p orbitals that are within the same axis between the atoms. So if we have our 2 atoms like this, the p orbitals that are within the internuclear axis will combine in a head-on interaction, in a sigma interaction. So you can kind of see here, like if this is one of our atoms, here's another one of our atoms, each of these is px, they will interact in a head-on interaction. But like all combinations of atomic orbitals, number of atomic orbitals you put in equals the number of molecular orbitals you get out. So to describe these 2 p orbitals interacting, we have to produce 2 molecular orbitals. So in this case, you see it's head-on, so it's a sigma. It's a sigma interaction. So we see the bonding, okay, so this one. The bonding description, so this is when the p orbitals are in phase. So you can see here, we have our atom and our atom. So where the head-on interaction, it's occurring between these 2 lobes that are in the same phase. So they add or interact constructively. So this is our bonding. Oh, that's wrong. There shouldn't be a star there. Bonding. I will fix that. So this is our bonding interaction, sigma px. Why do we put px? It's because the interaction is between 2 px atomic orbitals. So we're just indicating what atomic orbitals are involved in this interaction. So we can take inventory of all of our p orbitals. So there is our bonding or our stabilizing interaction, and then we have to have the counterpart, the anti-bonding interaction. So you can see how these 2 lobes are out of phase. They're the different colors. So they will interact destructively. It's a destabilizing molecular orbital. So we get our anti-bonding orbital, so sigma star. And then we say what orbitals are involved, so it's px. All right? Okay, so that's one of the interactions that we can have. But remember, there are 3 different p orbitals. We have this one, we have this one, and then we have this one. So we can have side-by-side overlap. So we took care of, if we have px, py, pz. We took care of px. That one is the p orbital within the internuclear axis. Py is perpendicular to the internuclear axis. So this is the side-by-side overlap, both py and pz. So these are both pi interactions. So this is a pi molecular orbital. So same thing as before. They can either add constructively or destructively. What does that mean? It means in this constructive picture, the phasing is correct. So the electrons are like this, and they can be shared with the same phase. In the destructive picture, the phasing is different. So when they add, they actually cancel each other out. And so what you get is our anti-bonding, destabilized, destructive combination. So this is a pi star interaction. So really, there's a pi star py and a pi star pz, because one of the interactions is this way for py, and then one is this way, pz. So we're kind of just doing them together. And then we have our stabilizing constructive addition. So we have pi interaction py and pi pz. Okay, so those are all of the different interactions between p orbitals. We took care of all of them, py and pz. So px was a sigma interaction, py is pi, and so is pz. Assuming that your internuclear axis is on the x-axis, which typically we make it so it is. Okay. And so, yeah, I have the same thing here. So second set of pi orbitals come from pz orbitals. They lie perpendicular. And so essentially we get two sets of pi MOs, one from py, one from pz, and they are degenerate, meaning that they're the same energy. So now if we put together the MO picture, the idealized MO diagram for a diatomic molecule within the 2p block, it will look like this. So here is so this is only for valence shell, only showing n equals 2, or our valence shell. I think I have that in the corner. Yes, only showing n equals 2 shell. So we have our s orbital interaction that we already talked about, right? We have our sigma interaction 2s and our sigma 2s, sigma star 2s. But now what's new are our p interactions. So we have px, py, pz. So see how there are 1, 2, 3, 4, 5, 6 atomic orbitals between two adjacent 2p elements, and then we get 1, 2, 3, 4, 5, 6 MOs out. 6 in, 6 out. And so this is the different molecular orbitals we just described, where between our px atomic orbitals, we make our sigma and sigma star interaction. And remember how I said that sigma interactions, there's much more overlap. Those bonds are stronger, so you get more splitting. So I'll just kind of note that here, that more atomic orbital overlap equals more splitting. More splitting of, I'll just say like sigma and sigma star, or pi and pi star. All right, so since a sigma bond has much more overlap, the energy difference between its stabilizing and destabilizing antibonding orbital, it'll be more. So that's what you see here, that the sigma and sigma star splits way more than the pi and the pi star, because our pi interaction is side by side, that there's less overlap. So the constructive and destructive difference is less. So that's what we see here with our py and pz orbitals. We see the splitting here. And like I said, those two pi interactions, the ones going like this and like this, they're the same energy. They're just in different planes of the molecule. So you see that the pi interactions between the py and pz are degenerate. All right, and so you see here the antibonding molecular orbitals are higher in energy than the original atomic orbitals, while the stabilizing bonding orbitals are lower than energy. So this is our idealized MO diagram for a 2p molecule. So, if you wanted to predict whether any of these 2p diatomic molecules exist, just pick one of them, count up the number of valence electrons, and then just start filling up your MOs. So that's really how it is, and then calculate your bond order using the calculation or the equation. So this is basically an MO diagram template for any 2p diatomic molecule. But just kind of to throw a wrench into the machinery of the idealized MO diagram that I've just introduced, as we move from boron to neon, some things change. So the MO diagram as you move from boron, boron, carbon, and nitrogen have what's called significant sp mixing, meaning that a lot of interaction occurs between the sigma 2s and sigma 2p orbitals. So these orbitals, or boron, carbon, and nitrogen. There's significant mixing. And what this does is changes the MO diagram for these three diatomic molecules. So these are non-ideal MOs. So this is what I mean. So for oxygen, diatomic oxygen, fluorine, and neon, they have idealized MOs. So diatomic oxygen, fluorine, and neon follow this MO diagram that we just talked about. So maybe I'll write that here. So this is for diatomic oxygen, diatomic fluorine, and diatomic neon. Have the idealized MO diagram. But for boron, carbon, and nitrogen, there is significant sp mixing. So what that means is that the placement of the pi 2p and sigma 2p orbitals, they switch. So essentially what happens is that these two, this orbital, the sigma 2p and the sigma 2s, they mix with one another, thus making the splitting more. Remember how I said more interaction or more overlap, the more splitting you get? So because 2p and 2x are mixing with one another, they split even more. But what you see overall is that you see that the pi and the sigma bonding orbitals within the 2p atomic shell, they switch places. And this is for boron, carbon, and nitrogen, while oxygen, fluorine, and neon have the idealized version. So keep this in mind. So overall, this is the MO diagrams for all of the diatomics within the second period. So boron, diatomic boron, carbon, and nitrogen have significant sp mixing. So the bonding orbitals between the pi and the sigma in the 2p atomic orbital shell, they switch places, while in oxygen, fluorine, and neon, they follow our idealized sigma pi, pi star, sigma star order going up. While boron, carbon, nitrogen, because there's large sp mixing, it goes pi, sigma, pi star, sigma star. So this is just something you need to memorize. Actually, you don't really have to memorize it because chapter 8, 9, and 10, it's all open note for the final. So just keep this in mind that we have large sp mixing with the first half of the 2p block of elements. And so you can see here that we just did the electron filling for you. So for diatomic boron, we have six valence electrons. There's 6. All right, and so if you fill up the electrons using Aufbau's principle, you see that the bond order is 1 because there's 2 electrons in a bonding orbital. And none in antibonding, because these ones all cancel out within the 2s shell. So 2 electrons in a bonding orbital, so 2 minus 0 over 2, that gives a bond order of 1. And so what you see here, because of that large sp mixing, what happens is that both of those electrons, because of Hund's rule, they're unpaired. That we fill them because the pi molecular orbitals, because they're degenerate. Like any degenerate orbital, we fill them singly first, and then we start doubling up. And so that's what you see here, that diatomic boron is paramagnetic because we have 2 unpaired electrons. if we didn't apply sp mixing here, then you would predict that it's actually diamagnetic. So make sure that you keep in mind sp mixing. All right, and so we do the same thing for diatomic carbon. There's 8 valence electrons, and you see here 8, 10, 12, 14, and then 16. And so still large sp mixing. So for diatomic carbon, we still keep the same MO diagram. We just add 2 extra electrons because each carbon has an extra electron there. And so you see now we've completely filled our pi MO. And so you would predict that diatomic carbon would be diamagnetic with a bond order of 2. And then you see a similar thing for nitrogen. Again, just add 2 more electrons from our carbon example. It is also diamagnetic because those 2 electrons we add are going into a sigma MO, and so they're still paired. And then so diatomic nitrogen is predicted, its bond order is 3. And that goes exactly along with the Lewis structure that you would predict for a diatomic nitrogen molecule. That a nitrogen-nitrogen triple bond is one of the strongest bonds out there, and that's because there are 6 electrons in bonding orbitals keeping those nitrogen atoms together. All right, and so again, here's another example where MO theory just correctly predicts things that we already knew from Lewis structures. And so you see, but MO theory can also predict para or diamagnetism in molecules. That's something that VSEPR theory could not do, but we can do it with MO theory. And then, okay, so diatomic nitrogen. Now, if we move on to oxygen, fluorine, and neon, we now have the idealized MO diagram. Idealized MO. While boron, carbon, and nitrogen, these have, let's just say, deviation from ideal MO. So here, again, we are using the idealized MO as a template. All we have to do is just fill in the number of appropriate valence electrons. So for oxygen, diatomic, we have 12 valence electrons we need to fill. So there's 1, 2, 3, 4, 5, 10, 12. So there are 12 electrons here, but following Aufbau's principle, when we place the 11th and 12th electron, they're going into degenerate pi star orbitals. So we have to place them singly. So something that you see here that's a little weird is that now we don't have any more bonding orbitals to place electrons. So when we have to add 2 more electrons, we're putting them into antibonding orbitals. But based on our bond order equation, so if we did this for oxygen, our bond order would be equal to 1, 2, 3, 4, 5, 6. 6 minus, and then there's 2 electrons in antibonding orbitals, so 6 minus 2 over 2, that equals 2. So MO theory is predicting that diatomic oxygen is a double bond, but that's what the Lewis structure says too for diatomic oxygen, that it's a double bond. So it completely corroborates with our knowledge from chapter 7. And then the last thing here that is more powerful in MO theory is that it can predict paramagnetism. And so that's what you see here, is that diatomic oxygen, because those last 2 electrons that filled are going in singly in an antibonding orbital or in our degenerate pi antibonding orbitals. So diatomic oxygen, the oxygen you and I breathe, actually is paramagnetic. You would have never known that. Ooh, that is not the Lewis structure for oxygen. This is the Lewis structure for oxygen. There we go. So you would have never predicted that diatomic oxygen is paramagnetic from the Lewis structure. But based on its MO diagram, you can say that it's paramagnetic. And I think on the next slide I show the paramagnetism of liquid oxygen. So if you take liquid nitrogen, which has a slightly lower boiling point than liquid oxygen, you can actually pull gaseous oxygen from the air and turn it into a liquid. So if you put like a test tube in a vat of liquid nitrogen, you'll slowly start to collect liquid oxygen. So once you've collected like a couple milliliters of liquid oxygen, you can place it on a magnet. So that's what this picture is showing. And so if you pour liquid oxygen onto the magnet, you'll see it stick. And so that's just kind of showing you the paramagnetism of diatomic oxygen molecules. So we don't really interact with the paramagnetism of oxygen that we breathe on a daily basis. One, because we don't see oxygen. But with this demonstration, you can see clearly the paramagnetic properties of diatomic oxygen. Okay, and so continuing on with the trend with diatomic fluorine and neon, you just keep adding electrons to our idealized MO. So you see here with diatomic fluorine, if we calculated the bond order here, how many electrons are in bonding orbitals? 1, 2, 3, 4, 5, 6. 6 minus the number of electrons in antibonding orbitals, 1, 2, 3, 4. So 6 minus 4 over 2 equals 1. And so MO is predicting diatomic fluorine has a bond order of 1. The Lewis structure says the same exact thing. Okay, and then lastly, diatomic neon, which is a noble gas. So you might have already predicted that diatomic neon doesn't exist, and it doesn't. And the MO diagram proves that, because once you've filled up all 16 electrons that you see here, and you calculate the bond order for diatomic neon, you get how many bonding electrons? So 1, 2, 3, 4, 5, 6 bonding electrons minus how many antibonding electrons? 1, 2, 3, 4, 5, 6. 6 minus 6 over 6 equals 0. So diatomic neon does not exist. All right? Okay, so that is the trend of MO diagrams for the whole 2p block of elements. And what MO theory really does really well is it allows us to predict whether molecules exist or not through bond order, and whether molecules are paramagnetic or not. And so in this case, it showed that diatomic oxygen is paramagnetic, although we would never have gathered that from the Lewis structure itself, as you see here. Okay, one last slide. This is the MO diagram for carbon monoxide. So carbon and oxygen are both 2p elements, right? So total, how many valence electrons do we have to place? In carbon, there's 4. 1, 2, 3, 4. And then oxygens, there's 6. So 1, 2, 3, 4, 5, 6. So this is the MO diagram for carbon and oxygen. So as you see, there is significant sp mixing. Okay, there's significant sp mixing within the p molecular orbitals. So if we actually do the MO electron filling, there's a total of 4 plus 6 valence electrons that we need to place. And so that's what you see here. We see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 valence electrons that we have to place. So if we calculate the bond order, there's these inner 2s electrons, they just cancel, because there's 2 electrons in bonding, 2 in anti-bonding. So if we just look here at the bonding orbitals, there's 1, 2, 3, 4, 5, 6 electrons in the bonding orbitals, and none in our anti-bonding, which are up here. So 6 minus 0 over 2. So our bond order for carbon monoxide is 3. And we know that actually from the Lewis structure, if we drew it, right? So here's another example where the MO theory just completely agrees with everything that we learned in chapter 7. And so that carbon-oxygen triple bond is one of the strongest bonds out there. It requires over 1,000 kilojoules per mole to break all 6 of those electrons that are holding together the carbon and oxygen atom in carbon monoxide molecule. All right, so that's it with MO theory. Stick around and we'll talk about gases in chapter 9.